Hello, this is Noah Wistman with another video. In this case, this video will be an asynchronous class for a course that I'm teaching about covariance, confounds, mediation, and moderation. Um, in this video, I'll be discussing these concepts and describing activities for you to get your own thoughts involved, for you to be able to practice using some of these ideas to come up with your own examples. So the way this video will go is that I'll spend some time talking about the concepts that I previously mentioned, and then at various points, I will describe an activity for you to do, which will help you to elaborate on these ideas, and I'll give you a chance to pause, work on it, and then start playing the video again. If you pay full attention and really try the activities and put your full effort into them, you really can get a similar amount out of this asynchronous class as you could with the in-person class, in-person version of the same class. But the main issue with asynchronous classes is that it's easier to check out and not pay as much attention. Even if you watch the whole video, do the activities, you're not quite as engaged as you would have been if the class was in person. So with that in mind, try your best to stay focused, pay as much attention to this asynchronous class as you would to the in-person class, and work on the activities to the best of your ability. If you do those things, then you really can get the same amount out of this class as you could with the one where we'd all be together. Okay, so with that said, let's get into it. As I mentioned, the topics that are being covered in this class are covariance, which is a very important concept in statistics. It's sort of at the heart of any kind of comparison that we want to do in statistics. Then there's going to be confounding variables, or confounds for short. There's going to be mediating variables, which have a mediating relationship. And there's going to be moderating variables, which have a moderating relationship. Okay. This topic is being given in the context of a previous class that we did, where we talked about the independent and dependent variables, also known as the predictor and the outcome variables, and often abbreviated to the independent variable IV and the dependent variable dV. Okay. And we talked about how these two kinds of variables here are kind of ways of thinking about the things that we're measuring in our study, the variables that we have in our study. Where we want to know what the independent variable is doing to the dependent variable. If it helps us predict things about the dependent variable, if it helps us to understand things about the dependent variable. Last class we gave a couple of examples of possible independent and dependent variables. This, for example, could be something like we want to know what someone's age does to allow us to predict their height. As their age increases, does their height also increase? If you were to go back in time and look at them as they're younger and younger, would we see their height decreasing? When would that be true for? When would it not be? Okay, well, the topic that we're talking about today is very much related to this topic here, in that these are kind of other kinds of variables, other ways of classifying variables. We talked about the independent variable or the predictor variable, the dependent or the outcome variable. Now we're talking about confounding variables and mediating variables and moderating variables. What makes these types of variables different on sort of a technical and conceptual level is the way that they relate to this idea of covariance. How we think about their relationship to covariance, how they interact with the idea of covariance. That's what allows us to distinguish these particular ideas. Okay. So with that overview kind of completed, what I'll invite you to do now is just go ahead and write down your questions and thoughts about this topic. This is sort of our first activity. And you don't need to write anything conclusive, just based on what you know about this topic here, what these things kind of sound like they might be. You can look up the definitions briefly if you like. Just write some thoughts and questions that you have about this topic before we dive into it. Go ahead and pause the video and take, say, 5 minutes to work on that. Okay. Hopefully you paused the video and you are now back. Of course, if you want to, you can complete all of these activities at the end after you watch it through. That's fine as well. Okay, so to begin this presentation proper, I'll start by talking about what I mean by covariance, because this is the idea that really frames the rest of the ideas that we're going to be talking about. So what is covariance? What do I mean when I say covariance? Why is it important? Well, I'm going to give an explanation of covariance that's relatively simple. It's relatively straightforward. Covariance is a fairly deep idea in statistics, much like variance in general is a fairly deep idea in statistics. I'm going to present a relatively straightforward version of this idea so that we can then relate it to these ideas right here. And so that we can then branch out from that simple explanation to more nuanced explanations as we continue to learn more about statistics and statistical methods. But for now, I'm just going to give kind of the 101. Okay, so one of the easiest ways to talk about covariance, to demonstrate covariance, is by making a scatter plot. We learned briefly about the scatter plot when we covered different kinds of plots that can be made in statistics. And the scatter plot is a particularly useful graph when you want to show a comparison between two variables, or two or more variables. Especially between two variables, though. And because of that, I'll be using scatter plots a lot for this demonstration, but also for future demonstrations of things like linear regression. It's just a useful kind of graph. So let's go ahead and make a scatter plot. And as I make it, I'll sort of refresh you on what the different aspects of a scatter plot are. Okay. So a scatter plot has two axes, one here and one here. And one of these, of course, is going to be the y-axis, and the other one's going to be the x-axis. Hopefully this is familiar to you from whatever algebra class you took in the past. Now, if we were doing algebra, we might be satisfied with just having y as our variable here and x as our variable over here, but when we do statistics, we are always measuring something, and we're comparing something that we're measuring to something else that we're measuring. So let's go ahead and come up with an example of something that might be our y variable and something that might be our x variable, keeping in mind that we could pick all kinds of things as the examples. We're just going to pick some that are relevant to us right here. Okay. We can use the example that we had before, and we can say that age is going to be our y variable, and height is going to be our x variable. That makes sense to me. Okay. And what we want to know is as your age increases, let's go to 1-year-old, now you're 2 years old, now you're 3 years old, now you're 4 years old, etc. 5, let's go up to when you're 7, just for fun. Okay. As your age increases in years, what happens to your height? Well, here we'll say that you're 0. Once again, here's our 0 point. We'll say that you're going to be 1 foot tall, 2 foot tall, 3 foot tall, 4 foot tall, 5 foot tall, and 6 feet tall. Okay. So hopefully you can see how we've set up these axes. And now let's say that we go and we measure some people. We ask them, how old are you? And we say, okay, now we're going to measure your height. Of course, because of the length of this axis here, we can only measure people up to the age of 7. Just that's all we can display. Okay, so let's say we measure some people, and for their age, which is our y variable, we get a couple of numbers here. And we get corresponding numbers of height for everyone that we measure. Just for the sake of sort of display consistency, let's say that after we measure everybody, we organize them from lowest age to highest age. That makes sense to me. Okay. So let's say that we got a 1-year-old here, and that 1-year-old was about a foot tall. Okay. Kind of weird to think about someone's height at that age since they can't even sit up, but okay, that's a foot long. All right. Let's say we got another 1-year-old, and they were also about a foot long. We got a 2-year-old, they were about 1.5 feet long. We got a 3-year-old, they were kind of 2 feet long. We got another 3-year-old. Oh, they happened to have a bit of a growth spurt. They were 3 feet long. Okay. And we keep going like this. We got a 4-year-old. The 4-year-old was also 3 feet. Okay. Maybe they were 3.5. Okay. We find people. We measure them. Makes sense. Okay. Now, what we're going to do on this scatter plot is we are going to plot these people on these axes. Okay. Let me switch colors just to demonstrate. So we have here someone who's 1 year old and they are 1 foot tall. So their point is going to go right here on the meeting between 1 and 1. We have a second person who's 1 year old and 1 foot tall. Let's put their point right next to that, right there. Don't quite have space. Both of them, that's okay. Now we've got somebody who is 2 years old. So we go up here for the age of 2. And they're 1.5 feet tall. So here they are in between 2 and 1. Great. Now we have a 3-year-old who is 2 feet tall. They're a little taller. They're 3. A 3-year-old who is 3 feet tall right here. Big tall guy right there. And we have a 4-year-old who is 3.5 feet tall. Okay. Great. Here we have constructed a miniature scatter plot. Now, in this scatter plot, we only have, 1, 2, 3, 4, 5, 6 points of data. We can imagine that if we did a more full study, we would have way more points of data than just 6 people. Okay. So let's say that we got some more people, we kept measuring them, and I won't go through all the trouble of writing all the values out, but we get a point that's here, and we get a point that's here, and just again, imagine we're measuring more people, and I'm just filling out the kind of graph here with all the different people that we managed to get. Okay. And we got people this old, etc. Okay. And we wind up with something that looks kind of like this for people's height. We can see that as people get older, between the ages of 0 and 7, they tend to get taller, which makes a lot of sense. Okay. What we have just demonstrated right here is positive covariance. Okay. What do I mean by that? Well, what we mean when we say positive covariance is that as age increases, as it varies upwards, so to speak, so too does height increase. It also varies sort of upward. Now, it's not a perfect relationship. You can see that some people who are older are a little bit shorter than other people who are the same age. You have people who are a little bit older who are nonetheless shorter than people who are younger than them, and so on like this. It's not a perfect one-to-one relationship, but in general, as age is increasing, height is also increasing. Okay. A lot of statistics and statistical analysis is about trying to explain how these points end up where they end up. In this case, we have a nice straightforward relationship where as age increases, height also increases. Sometimes we won't have this straightforward of a relationship, but in this case, this is a pretty clear example of positive covariance. Okay. Now, real quickly, without doing the whole drawing out thing, let's go ahead and give myself some space over here. Sorry, data points. Okay. Let me show you quickly, without going through as much trouble as we went through before, what negative covariance looks like. Okay, so here we have some y variable, we have some x variable, and we're going to have some numbers here that are going up, some numbers here that are going up. Doesn't matter too much what they are. Go ahead and think about what negative covariance would look like. If positive covariance is when x is increasing, y is increasing, and when y is increasing, x is increasing, what would negative covariance look like? Well, in negative covariance, as y is decreasing, x would be increasing. It would look something like this. Okay. Again, doesn't need to be a perfect relationship. In statistics, we very rarely have perfect straight line relationships. But you can see here that as y decreases, it goes from 5 to 4 to 3 to 2 to 1. X tends to increase. It goes from 1 to 2 to 3 to 4 to 5 to 6. And this is an example of negative covariance. With covariance, the term covariance just referring to the fact that as y varies, x varies along with it. In this case, as y varies sort of upwards as it tends to increase, then x tends to increase as well. The variance is going up together. Here, as y decreases, x tends to increase. They're still varying together, they're just varying in sort of the opposite direction. It has a sort of downwards trend on our scatter plot here. Okay, so in very simple terms, this is what covariance is referring to. When y does something, does x also do something? That's sort of a noticeable pattern. Does it also increase? Or when y goes up, does x go down? When y goes down, does x go up? As long as there's some kind of consistent pattern in the variation between the two variables that we're looking at, we can say that there's some kind of covariance, either positive or negative covariance. Okay. Also important to note, again, I'll do this at a small scale, and we'll talk more about this when we talk about linear regression, but the more condensed the line is, so to speak, assuming that we get a kind of straight line, the stronger the covariance is said to be. By contrast, the more kind of spread out the line is, the more spread out the data is, the weaker the covariance is said to be. This would be a case of very high covariance. This is a case of very low covariance. It might be so low that we're not even really willing to call this covariance. It's barely anything if it's anything at all. Okay, but we'll talk about this more later. Now, what I've just shown you here is covariance between one independent variable and one dependent variable. But if you remember, I mentioned in the last class that we can have multiple independent variables. We can have multiple dependent variables. And we can also have lines that aren't straight. Right here we've seen these kinds of covariances where there's a kind of general straight line trend going on. But we can have lines that aren't straight. We can have all different kinds of distributions. We can have more variables, more complicated setups of our variables. And all of these things will make thinking about covariance more complicated. Covariance will still be a concept in those different situations. It'll just be a harder concept to fully get a grasp on. But the basic points will remain the same. We're looking for when one of our variables changes, does the other variable change along with it? Or is there no pattern that we can notice? Okay. So this is our introduction to covariance. Again, as demonstrated by these scatter plots. We'll be talking more about this when we talk about regression, which is a really natural expression of these concepts. That's going to bring us to our second activity here, second opportunity to pause the video. In this case, I'm going to ask you to come up with one independent variable and one dependent variable. And you can reuse an example that you thought of in the past if you already have that in mind. Go ahead and draw a scatter plot which shows what you think the relationship between these two variables would be. Again, don't worry about if it really is that relationship. We're not doing a full study here. We're just trying to use our brains to think about this a little bit. Draw a scatter plot and describe their covariance in, I'm going to call it regular talk. What do I mean by that? Okay. Well, if I was just to describe this graph here in regular talk, I would say as age increases, as people get older, as age increases, they tend to get taller. That's a kind of normal English sentence that would result in a description of this graph. Over here, I would say, well, as y gets lower, x gets bigger. Some description that's like that. Let's say I have a little bit of a fancier distribution. Maybe I decide I want to plot something that I think would look more like this. For example, something like income often has this kind of trajectory where you start your career, you're making very little money, then you make the most money in the middle of your career, then you start slacking off a little bit, thinking about retirement, and you make a little less money towards the end, and then you're not making very much when you're in retirement. In this case, in regular people talk, I would describe this as, there's sort of a general trend upwards, and then it flattens out, and then it declines. That's the kind of sentence that we want to use to describe the scatter plot that you draw. Okay. So go ahead and pause the video, come up with an independent variable and a dependent variable, draw a scatter plot which shows what you think their relationship would be, doesn't have to be exact or anything, then describe the kind of covariance that they're demonstrating just in regular terms. Okay, go ahead, take a crack at that. Okay, welcome back. Hopefully you had a good time with that over there. Okay, let me do a little bit of resetting here of our space here. And I'm going to erase this just to give myself more space. Make sure that you have a good idea of what negative covariance looks like before I get rid of it. Okay. Now, let's continue. Let's go back to our original example here of age and height. We're saying that height tends to increase as age increases. Okay. Well, now that we've established what covariance is, we can think a little bit more about these ideas over here of confounding variables or confounds, mediating variables, and moderating variables. Okay, what are those ideas all about? Well, let's start with the idea of a covariate. Okay, we've talked about what covariance is, this idea of things are going to change together. Well, what is a covariate? And this is a little bit difficult to describe in a general sense, but in a really like just basic one-word sentence, covariate is any variable that we want to add into our model, which is not our main variable, but that is still a predicting variable. Okay, what does that mean? Well, right now we're comparing an independent variable of age, and we're looking at it in relationship to height. But let's say that we wanted to look a little bit more deeply into this situation. We didn't just want to know what age was doing to height, we wanted to know about some other stuff at the same time. Let's say that we also wanted to know what, say, nutrition has an effect on height. We want to both look at height in terms of age, but also in terms of the kind of food that these kids are eating. In this case, we might expect that someone's age is a very strong predictor of their height, much stronger than nutrition would be. A child who's 1 year old, who is not getting very good nutrition, who's getting very good nutrition, is still going to be shorter than a child who's 2 years old who is getting good nutrition, just because they had a whole another year to grow, the child who's 2 years old. So in that sense, we might expect age to be the stronger predictor, but nutrition should also be an important predictor as well. In this case, age would be considered our sort of main independent variable or main predictor variable, and nutrition would be our covariate. Okay, and covariate is, again, it's sort of a generic term for any time we want to add in a second, a third, a fourth predicting variable, but that we wouldn't consider to be the main one that we're looking at. That's a sort of generic definition of the word covariate. Okay. Now, let's say that we introduce nutrition as our covariate, nutrition. And just for the sake of simplicity, let's say that we have 3 categories of nutrition, like 1, 2, and 3. Where 1 is you're getting poor nutrition, that's poor, and 3 is you're getting good nutrition. Okay. Obviously, we could have this be a continuous variable, and that would make displaying its effect a little bit trickier, which is why I made it a categorical variable here, but just note that this could be continuous if we wanted, and we'll talk more about that when we get to regression. Okay. And let's say that we found that people who were getting poorer nutrition were tending to be a little bit shorter than people who were getting better nutrition at the same age. So for example, these people are all 3 years old, but we find that this person's getting poor nutrition, this person's getting decent nutrition, and this person's getting good nutrition. And we do the same thing for other heights, and we find that, hey, these people are all 4 years old, but this is their nutrition breakdown. And we also find some things that don't quite match that trend. They're not all in perfect order. Here we have someone who has good nutrition who's 6, who's a little stronger than someone with fair nutrition. But in general, we find that people who have poor nutrition are turning out to be a little bit shorter than people who are the same age who are getting better nutrition. Huh. Very interesting. This would be an example of a useful covariate here. Okay. Now, in general, covariates can have, I would say, basically 3 different kinds of relationships with our sort of main variables. They can either have no relationship, they can have a mediating relationship, or they can have a moderating relationship. Okay. What do these mean? Well, if a covariate has no relationship with our independent or dependent variable, what that means is that we introduce it, and boy golly gee, it just doesn't come up with anything. We go through all the trouble to measure some other aspect of a person, to try to predict, for example, what their height is, and it turns out that it just doesn't have any effect. An example of this might be something like, let's say that we want to look at something like exercise. We think that, hey, maybe the amount of exercise a kid is getting is related to how tall they're getting. So we look into it, we look into how much exercise people are getting, but we find, wait a minute, there actually isn't a relationship between exercise and how tall someone ends up being. Whether the kids are getting a lot of exercise or they're only getting a little bit of exercise, it just doesn't seem like anything's really going on there. In this case, we've introduced this covariate, but it hasn't been a very successful covariate for us. It has sort of no relationship, or such a weak relationship we really can't make much of it. This is generally considered to be a bad thing because we've invested extra time into measuring this, and it hasn't really returned anything positive for us. Okay. Next, I'll talk about a moderating relationship, because this is the kind of relationship that we might say that nutrition has, and this is sort of the example we used before. Nutrition has a moderating relationship because it has an effect on height. It sort of influences height, but it's not, you wouldn't say that it is directly related to age in the same way. The way that this is usually expressed is that we have age over here, go for A for age, and this is having an effect on height over here, and the level of nutrition that people are getting is kind of getting involved over here. It's having a moderating effect on the relationship between age and height. Okay. Very interesting. Now, what then would be an example in this situation of a mediating relationship? Well, in a mediating relationship, rather than having some kind of direct effect of our independent variable on our dependent variable, which is being influenced by a third variable that we've introduced, in a mediating relationship, there's something that's getting kind of in between the relationship of our independent and our dependent variable. For an example of that, we might look at something like cell generation. or cell division, the process by which our bodies make new cells. In this case, we can say that as people are getting older, this is causing them to go through more cell division, which is in turn allowing them to get taller. Okay. So, if we could measure someone's rate of cell divisions, we might be able to predict their height better than if we just measured their age. But obviously, it's a lot harder to measure cell division compared to measuring their age. In this sense, cell division can be thought of as having a mediating effect between age and height. We're measuring age to predict height. What's really going on is that more cells are being created in a person's body. And so, in that sense, cell division is the sort of true cause of someone's height. It's a mediating variable for which age is just a proxy. Okay. Don't worry if you didn't 110% follow everything I just said here, because again, we'll have more opportunities to talk about when we talk about regression. And this concept here of the difference between moderating and mediating relationships and variables is often very tricky to get, and the differences between those kinds of relationships are often more nuanced than we might like to believe. For example, I might be able to make a case that nutrition should be thought of as a mediating variable between age and height because you need to eat food in order to grow at all. After all, what is fueling all the cell division except for the nutrition that you get from the food that you're eating? When we created this nutrition scale, we were comparing people who were eating but just not eating very well to people who were eating very well. If we included as another measurement of people who weren't eating at all, we might find that nutrition has a very important causal mediating relationship between age and height. You gotta eat as all that time is passing to grow taller. So again, it's a little bit unclear often what exactly is a mediating variable, what exactly is a moderating variable, what is a covariate, what should count as a covariate, and what shouldn't. This is a very real problem that happens in real statistical analyses, and I think the most important thing to remember, rather than the very specific differences between these factors, is this idea of covariates and covariance. To give another kind of example along these lines, you could easily have a situation where something that you consider to be your main independent variable winds up being not as strong as a predictor as something that you introduce as a covariate. In which case you might think to yourself, well, maybe I should switch and I should make what I thought was the covariate into the main independent variable, and what I thought was the independent variable into a covariate. So again, it's all very kind of fluid, nuanced, not so clear in practice as it is on the piece of paper. That's okay. We just want to get a handle on these ideas, start considering them. Okay. Now this brings us to our third activity. For the third activity, go back to the example you made for the second activity. Okay. Come up with a possible mediating covariate and a possible moderating covariate. Then draw the chart like I drew in the example for both. Okay. So basically I'm going to ask you kind of to look at your own example and do what I just did over here, where I came up with two possible covariates in nutrition and the creation of new cells. And I drew a little bit of a chart here for the moderating relationship, where nutrition has a moderating effect on the relationship between age and height, and cell division, the creation of new cells, has a mediating relationship. Again, don't worry too much about if you get which one's moderating and which one's mediating exactly correct. Just make sure you come up with two reasonable covariates and you understand where they fit into the picture between your independent variable and your dependent variable. Okay, so go ahead and pause the video, work on that, and we'll come back for our last topic. Okay, welcome back. Hopefully that went well for you again. I just want to mention before we begin our last topic here that, once again, we are looking here at a situation where we've introduced, one moderating variable and one mediating variable to our overall model, but we could easily have a third one, a fourth one, a fifth one, a sixth one. We could just keep going. Statistical models can get very complicated and very involved if you want them to be, if you want to make something that's fancy, and in modern research a lot of people do make very fancy models, but the basic principles that we're discussing here continue to apply in those more advanced models. They just get a little more complicated and more involved as well, but the core of it remains the same. Okay. With that said, let's talk about our last main topic for the class here. And this is the idea of a confounding variable, or confounding variables. And this idea is a little bit tricky. Basically, again, just in one sentence, off rip, a confounding variable is a variable we aren't taking into account. That could be affecting things. Okay. Let's go back over here. In this case, you can see that we have one of our variables of age, and we found a way to measure people's ages. We just asked them how old they are. We got another variable, height, and we had a way to measure people's heights. Over here, we have nutrition. We found a way to measure nutrition. Over here, we have cell division. Let's say that we found a way to measure people's cell division, the rate they create new cells at. In all of these cases, we've introduced these variables, and we've said that we have some way of measuring it, some way of including it in our model of trying to predict how tall people are going to be, or explain how tall people are. Okay, but invariably, inevitably, there's going to be things that are more difficult to measure that we can't get around to measuring because we only have so much time, we only have so many resources in our study, and those things might very well be contributing to the variation between our variables, our main variables, and we just aren't getting around to measuring them. To use this example here, we talked about how maybe we could factor in cell division, exercise, nutrition. Of course, we're already looking at age, but we didn't look into something like, let's say, somebody's gender or their sex. Does that have an effect on the rate at which they grow? Well, maybe it does. Well, hey, maybe we could factor that into our model pretty easily. We would just have to ask people, what sex are you? What biological sex are you? And then we could factor that into our model. Okay, but then we might also want to know something like, what season were you born in? Do winter babies tend to grow taller than summer babies? I don't know. Maybe they do. Seems like there could be an argument for that. Okay, well, we looked at nutrition. We said 1, 2, 3. what if we wanted to look at something like dairy consumption specifically? And we want to know specifically, does consuming dairy have some kind of relationship with your age and your height? Well, that might be hard to figure out. We ask people about their nutrition, it might be harder to get information specifically about the dairy that they ate. Similarly, we could ask, well, what about like protein consumption? What about carbs? We could break down nutrition into more specific information. All of these are things that in the model we presented over here are things that we weren't taking into account that seem like maybe they would be able to affect things. What about something like whether or not you had an early childhood disease? Whether or not your parents are smokers, how much they smoke, or whether or not they're drinkers as well. All of these are things that might be hard to get access to. Maybe, for example, it would be difficult to get people's parents to admit to doing these kinds of things. Maybe they don't trust us to keep that information private. Okay, and all of these are just variables that we just didn't take into account when we were putting together this model over here. These are known as confounding variables. They're a little bit weird to think about because, like, by definition, they're things that we're not measuring. They can't possibly be factored into our statistical model to see what kind of influence they have because we, by definition, aren't looking at them. But they're important to think about because they affect our interpretation of whatever our statistical model is that we built is. We might like to say that we've got it all figured out, but as long as there are confounding variables out there that we haven't looked at yet, we've got to stay humble and we've got to say, hey, this is the relationship between the variables that we found, but there's plenty of confounding variables that we haven't looked at, or possible confounding variables that we haven't looked at, and we don't really know what's going on with them. Okay. Kind of functionally, in practice, let's say, confounding variables often act like a disclaimer. They're a way for us to say, hey, this is what we found, but we're not sure because of these reasons. Okay. This is a major issue, this issue of confounding variables, possible confounding variables. Whenever you're studying people, in any of the social sciences, in any kind of business or legal setting, anything that involves people interacting with other people, it's a big issue because there's almost always just an endless list of possible confounding variables. Here we're comparing something as simple as age and height, and we were able to come up with all of these possible confounding variables that we haven't looked at, haven't factored into our model. Imagine how complicated this can get for something like someone's educational performance, something like someone's decision to commit a crime. There's all kinds of things that play into that are difficult to measure, that are nuanced, that affect each other, that are hard to incorporate into our statistical model. And so this creates a problem of being able to trying to interpret results that we know are limited, and we're going to talk about that later when we get to a class about the problem of interpretation, focusing exclusively on that issue. Okay. So that brings us to our last activity here. And for this activity, relatively straightforward, I'd like you to go back to your example that you came up with earlier and just list 5 possible confounding variables that you didn't factor into your model before, but that might be important to it. Keep in mind that if you were to go out and measure one of these things and bring it into your model, then it would no longer be a confounding variable. It would just be one of the variables in your model. It would just be a covariate. Oftentimes when people do actual research, they will do exactly this. They will realize that something is potentially missing from their model, they'll go and measure it, and they'll bring it into their model. Things that stay confounding variables that aren't quickly incorporated into models tend to be things that are hard to measure, that involve sensitive information that people don't want to give out necessarily. They're things that are subjective in some way. All of which is to say, try to think of things that fit into those kinds of categories, things that are difficult to turn into variables that we're actually measuring. Okay, so go ahead and just list 5 possible confounding variables for the example you made before. Now you can pause the video, come back when you're finished. Okay, welcome back. Hope that went well for you again. And, as I've been saying before, don't worry about if your models or your examples are totally perfect. We're just trying to interact with these ideas and think a little bit more about them. Okay. So that concludes the presentation here about mediating, moderating, covariance, confounding variables, all of these ideas. And just a sort of general recap, remember that all of these are ways of talking about the variables that we have included in our study, and they're ways of conceptualizing the relationships that we are seeing between those variables.